Should I start?
Mm-hmm.
Okay. Okay. So welcome everybody. I'm Debasis Mitra, the host of this webinar, and it's sponsored jointly by the Sense, Collect, and Move Data Center within the DSI and the Electrical Engineering Department. Our speaker is Irving Kalet, and the topic is 6G, specifically modulation in 6G. A quick word about Irving, who's also my colleague and friend. He received his PhD in electrical engineering from Columbia in 1969, a generation or two ago. His advisor was Bennett. He went to work at Bell Labs in Homedale in the data theory group. In the 1980s, Irving's manager at Bell Labs was Victor Lawrence. And Victor affectionately recalls Irving as a peacemaker and a historian. That reference to peacemaker needs a little explanation. At that time, DSL was a young, growing technology, and there were a number of competing solutions and a lot of heavy, big guns in the field, in electrical engineering communications, were pitted against each other. And Irving published a now well-known paper in the IEEE Transactions in Communications in 1989. And the title was Multi-Tone Channel. And it settled a number of technical issues. I mentioned this especially because the topic today is also modulation. That's all I wanted to say about Irving. A quick word about the webinar protocol. By the way, Irving happens to be right now in Israel. The downside to this wonderful technology is the participants can't speak. So your questions will have to be typed in the Q&A window that you see. And at the end of his lecture, Irving will read out the questions and respond to them. Thank you. It's all yours, Irving, now.
Thank you, Debasis. First, hello to everybody. Right now where I am, it's night, but good afternoon to the rest of you. So far, it's been an interesting day for me. We're under lockdown in Israel for the second time, and some of us are even demonstrating. So about 2 hours ago, I was at a demonstration against the head of the government, which some of you may be able to identify with in the States. But anyway, we'll get down to the business here. The title of the talk is 6G. Yes, 6G, the radio interface, basically about modulations. I got interested in this topic because in general, I'm interested in modulations. But about a year ago, somebody asked me to give a talk to a consortium here in Israel about the 5G OFDM modulations. And I gave a talk, and I figured at the end I would try and say something funny and say something about something called 6G. I didn't even know there was anything called 6G. And I was going to just say, well, now next year we'll talk about 6G. Well, I got on the internet, and it turned out that 2 months earlier in March, there had already been a conference in Finland about 6G. And in the last year, almost every month, even faster than that, an article comes out about something called 6G. Nobody knows what it is yet, but they more or less have an idea of what they want it to be. So this talk is about something that really doesn't exist yet, but people are starting to talk about it. Not only starting to talk about it, there are many conferences. We'll talk about that later on. A lot of companies, a lot of universities working already on 6G. Okay, so let's begin. First of all, what I'm going to do at the beginning is give a brief review of the modulation techniques for 1G, 2G, 3G, and 4G, and then 5G, just as an introduction to what we might expect from 6G. And what we might expect from 6G later on, we'll see, is something different than we've seen in the last 10 or 15 years. It looks like OFDM may be going out of business, partly out of business. So we're going to first describe a little bit of the history, and then we'll talk about why 6G now and some of the background, and then some of the modulation proposals which already have been made And I'm talking about things that are happening right now. In fact, I put something later on, one of you graphs. It was an article that came out in September, less than 2 days ago. Okay? First of all, a little bit of history. The play on words is the idea of my advisor, W.R. Bennett, used that when he, in one of the courses, to describe a little bit of history. Let's start off and take a look at the different generations of cellular communications. Cellular communications started coming in to being around 1980. The original reason was basically for people who were having trouble on the road. The typical problem was going to be what happens if a woman in 1980, a woman couldn't change a tire. So what would happen in 1980 if a woman's stuck on the road, has a flat tire, and she wants to call up, and she has no way of calling up? So this was supposed to be one of the first uses of the first generation of cellular communications. I won't go into the whole topic of why it's called cellular communication. I think most of you know that. But the first generation was basically an analog system, analog FM. Bandwidth was around 30 kilohertz, and I think in Japan it was 25, but in the States it was 30 kilohertz. FM, and I want to mention this right, FM is a constant envelope signal. Constant envelope, constant amplitude means you can use a non-linear power amplifier in the handset, and a non-linear power amplifier makes efficient use of battery power. So it's if you could use a non-linear power amplifier, you get efficient use of battery power, and you can do that with a constant envelope signal. Constant envelope signal only has one amplitude, so even if it's a non-linear amplifier, it's one amplitude goes in, one amplitude comes out. An AM signal, for example, amplitude modulation has different amplitudes. If you have a non-linear modulation, you change the amplitudes non-linearly, and you also increase the bandwidth. Again, the first generation was based on FDM, frequency division multiplexing, and divide up the frequency band. Every 30 kilohertz, you put in a user. Okay, second generation, about 10 years later, 1992, the second generation already becomes digital. Maybe one of the biggest advances was in Europe. In Europe, it turned out a lot of the first generation systems in different countries were different systems. So if you wanted to go from Germany to England, you had to change your phone. And the basic idea, at least in Europe, as part of the unification of Europe at that time, was to try and have one uniform system throughout at least Western Europe. And so they came up with a system called GSM, which originally meant Groupe Spécial Mobile, a French name. And somebody a few years later decided it's easier to market in English. So it became Global System for Mobile Communications. It's a digital system, send bits. So the digital system, the modulation technique they used was something called GMSK, which we're going to see later on. Gaussian MSK, operated at 270 kilobits per second, but GMSK is also a constant envelope signal. It's essentially a digital FM signal. Again, one of the reasons for using that, efficient use of battery power, and if you're holding, if you're holding the amplifier in your hand as a telephone, you would like to charge up the telephone every month instead of every night. So you'd like to make efficient use of the battery power. Just to sidelight, the 200 kilohertz was the bandwidth of the signal, had 8 users inside 200 kilohertz, so about 25 kilohertz per user, based on TDMA, time division multiple access. In the United States, the idea was also go to TDMA. Again, digital communication with transmitting bits from one place to another. This was analog. Now we're in digital. In the United States, basically, the FCC at the time wasn't willing to give a industry more than the original 30 kilohertz that they had over here. And so basically what happened is the idea was to put in 3 users in 30 kilohertz instead of 1 user in 30 kilohertz, tripling the capacity in the United States. The modulation technique was pi over 4 QPSK, had a roll-off of about 35%. Pi over QPSK is not a constant envelope signal, but pi over 4 QPSK, they try and at least make it have a less amplitude fluctuation. So even here, the idea was to try and reduce the peak to average ratio, try and make more efficient use of the battery. Okay? In this case, talk about tens of kilobits per second here, 270 kilobits per second. And then also in the second generation, we had the introduction of CDMA. Without going into what CDMA is, the bandwidth was 1.25 megahertz, using 1.2288 mega chips per second. And the original idea, again, was to transmit voice using vocoders, converting the voice into 9.6 or 13 kilobits per second, and then transmitting it using CDMA. Here they were using a 13 kilobit second vocoder. Here there was an 8 kilobits per second vocoder. But in all these cases, you're taking voice and converting it into bits. Digital communication, digital system. But the main reason for all of these was voice communications. There was an attempt made here, especially here, to introduce, for example, now it sounds almost ridiculous, the introduction of email, introduction of actually transmitting bits from one place to another. And mainly, again, the use here was to transmit voice, but when you had to take the voice and convert it into bits. But transmitting email meant already you just information was in bits already. But these are all digital systems. Okay? The second generation, 1992, you're talking about tens of kilobits. And in this case, the actual transmission of 270 kilobits, but information was also tens of kilobits. Third generation, we went to something called wideband CDMA. A wideband CDMA, and without getting involved in what CDMA is, 3.84 megachips per second and a bandwidth of 5 megahertz. Again, using signals which had 22% roll-off. The data rates here originally supposed to go up to 2 megabits per second, but that started off with 384 kilobits per second. A wideband CDMA, in this case, is not a constant envelope signal, and we start having trouble with peak to average here. Okay, now, third generation, we start to go to the fourth generation. Okay? Between the third generation and the fourth generation, they introduced something called 3G LTE. 3G means third generation, and LTE means long-term evolution. The basic idea was, in the name, was, okay, they were going to start to change the third generation, but it really wasn't long-term evolution. It was really a revolt because they changed the complete system that went from CDMA to OFDM, OFDMA. And so it was really a revolution and not an evolution. So during the third generation, there's a movement, and they eventually do it, to convert to 3G LTE. 3G LTE is based on OFDM, OFDMA. The downlink was OFDM. The uplink was based on something called single carrier FDMA, which is sort of based on the same technology, but has a lower peak to average. But here, we talk about OFDMA, and we'll describe OFDM a little bit for those of you who don't know what OFDMA is. We're talking about transmitting lots of narrowband signals. And the second you're talking about transmitting lots of narrowband signals, high peak to average, very inefficient use of battery power. Inefficient use of battery power. Keep in mind, first generation, second generation, there was a real interest in trying to preserve battery power. Here, OFDMA, again, the sum of many, many signals, high peak to average. Okay? In this case, the maximum bandwidth was 20 megahertz. Originally, the highest they used QAM as the modulation. The highest modulation was 64 QAM. And again, in this case, 6 bits per symbol. Eventually, they went up to 256 QAM, 8 bits per symbol. Okay. The whole concept here was based on using FFTs, and inverse FFTs. And the whole concept is based on something called discrete multitone, which originally is based on an article written in 1970 by 2 people from Bell Laboratories, Paul Ebert and Steve Weinstein. So that was originally based on technology, from ideas from Bell Laboratories. Okay, fourth generation, about 8 years ago, fourth generation 4G LTE, again based on OFDM. Essentially, it's very similar to the third generation. We'll talk about it in a second. Again, maximum bandwidth of 20 megahertz, but maximum bandwidth for one 20 megahertz band. But you can combine bands, called something called carrier aggregations. Instead of using one 20 megahertz band, you can use 5 20 megahertz bands and increase the bandwidth. So here was a chance to increase the bandwidth by a factor of 5. Also started to use MIMO. I think in the standard, they talked about using 8x8 MIMO. I think commercially, the best ever was done was 4x4. But basically what MIMO is going to do is it's going to increase the bit rate by whatever this number is. It's increase the bit rate by a factor of 4. If you can go to 8x8, increase the bit rate by a factor of 8. And again, this was based on just transmitting lots of QM signals. Again, maximum size of QM was 256 QM. And here you're talking about data rates of hundreds of megabits per second. Fourth generation. Fifth generation, which we'll talk a little bit more about, again, based on OFDM. Keep in mind, 3G LTE, 4G LTE, and now 5G NR. Based on OFDM, in this case, they started to change, we'll talk about it in a second, they started to change some of the properties of the signal that was used here. We'll see how the change was made. But in this case, you can go from 20 megahertz up to 400 megahertz. Again, talking about using MIMO again, and talking about using QAM signals again up to 256 QAM. But here we're talking about data rates 10, 20 gigabits per second. Okay? That's 5. Okay, so 5G is right now. 5G coming into use right now, 2020, in different places throughout the United States, throughout the world. The idea was to try and get these tremendous bit rates, talking about 10, 20 gigabits per second, to try and satisfy many, many, many users. And the basic solutions is extreme, I mentioned extreme densification using lots of small cells. It creates a backhaul problem, how to get all that information back to some central location. But using lots and lots of small cells, to get very high bandwidths, you have to go up to high frequencies. And the idea now is to go past 6 gigahertz, go into the range of tens of gigahertz of center frequency. I think the maximum is 52 gigahertz. And much more bandwidth available at 52 gigahertz than there is at 1 gigahertz or 2 gigahertz. So sort of brute force solutions, use a lot of small cells, use a lot of bandwidth, and then advances in MIMO and massive MIMO, and then advances in some codes. But again, it's OFDM, OFDMA again. Why OFDM? Just a few words for those of you who may not be familiar with why OFDM. Why is OFDM such a popular thing? Because suppose I have a signal. Here's a typical, that's not a radio signal, but let's say a typical binary PAM signal. You have a typical binary PAM signal, you know, plus minus PFT. PFT is just a rectangular pulse. If I transmit the signal and part of my signal bounces off some building into my receiver, I get the original signal, and then I get another signal, which is essentially the original signal just delayed in time. And suppose the delay is around 6 microseconds. 6 microseconds would be a delay of around 6,000 feet in terms of distance. And suppose I'm using signals which have a symbol rate of a symbol every 4 microseconds, which would be the typical example of GSM, 270 kilobits per second. At the receiver, you would get the original signal, and then you get this other signal which is bounced off a building. And if you take a look at what you're getting, this second signal is going to interfere with these bits over here, and you have intersymbol interference. And basically what's happened is that each bit that you originally sent, which only lasted for T seconds, now, or in this case 4 microseconds, now lasts for 10 microseconds because I have this addition. And so you start having intersymbol interference. Instead of having a perfectly time-limited signal like this, which lasts just for 4 microseconds, all of a sudden each one of these bits spreads out in time and causes intersymbol interference. And we can overcome intersymbol interference. We know how to do that. But suppose I was to tell you that I can come up with a different system in which no matter what the delay spread is, I make this T so big that the delay spread is less than 10% of the time of a symbol. And so basically what happens, this little part here ends up in the next symbol. It really doesn't bother the next symbol. And so we say, you know, if it really doesn't bother, we're not going to worry about it. We're not going to build an equalizer and not worry about it. So basically, really what I need is that this time be much, much bigger than this so-called delay spread. And suppose I tell you that the delay spread has to be less than 10% of this time, then I don't have to worry about equalizing. I don't have to worry about delay spread. So what we can come up with is something, this is sort of very heuristic reasoning for using OFDM. We can think of sort of an example in which we have a QAM signal. And suppose we have a QAM signal operating at 20 kilosymbols per second. If it's operating at 20 kilosymbols per second, it means that the bandwidth is 20. If you're using Nyquist signaling with 0% roll-off, it means the bandwidth is around 20 kilohertz. But it means the symbol time is 50 microseconds. Suppose I tell you that the maximum delay spread in urban environment, which was true for the GSM model, is 4 microseconds, around 4,000 feet. This is less than 10% of that. And so I don't have to worry about delay spread. And so let's use 16 QAM. I send 4 bits every T seconds. I end up getting a signal which is operating at 80 kilobits per second and a bandwidth of 20 kilohertz. But then you say to me, but that's not a lot of bits. You know, I want to transmit megabits per second. So then you say, well, who says I have to just use 1 QAM signal? Why not use 256 QAM signals, one next to another, each one transmitting 80 kilobits per second, 256 times 80, 20 megabits per second, and a bandwidth of 5 megahertz. And I don't have to worry about equalizing the signal. So this is sort of the basic reason behind why everybody is using OFDM. Once you use OFDM, there are other good reasons for using it, but But the basic reason was this. And this is why it was so popular in 3G and 4G and even now in 5G. Okay? Well, the way we normally generate this kind of signal is by using discrete multitone, going back to this idea of using inverse FFTs and FFTs, originally an article in 1970 by Ebert and Weinstein. And basically the idea would be in a frequency domain, each one of these frequencies, sort of each one of these numbers represents a different frequency. And each one of these, for example, might represent a typical QPSK signal. If you think of it, a QPSK signal is 4 vectors. This would represent these, each one of these represents a different QPSK signal. And so each one of these represents a different signal. Then you do an inverse FFT, you go into the time domain. And then you have these vectors, I should say, these values in the time domain. Imagine pushing these out one after another through an ideal Nyquist filter with no intersymbol interference. And so basically in just using one inverse FFT, you could generate, take all these, so let's say 64 signals or 256 signals. One inverse FFT, you come into the time domain, you push these through some kind of low pass filter, let's say an ideal Nyquist filter, and you're transmitting the signal. And the only trouble you might have is that it turns out maybe at the very end here, if you had a Nyquist signal, part of this ends up into the next block because there's delay spread. So what you do is you just go to the next page. And what you do is you just leave a little room over here, leave a little room here between one block, one OFDM block, and the next OFDM block. So you can imagine if there's an OFDM block here, between this OFDM block and this OFDM block, I leave a little buffer. So if there's any delay spread, the delay spread doesn't end up in this block over here. And then it turns out we have to fill up this buffer to fool the whole system into thinking that it's a discrete system. And we fill this up essentially with the end of this OFDM block. And this is the so-called cyclic prefix, which allows us, first of all, put a buffer in, and also allows us to use FFTs and DFTs on both sides. Just to go back go up for a second. If we come back over here, the difference, this difference in frequencies, which essentially represents tone spacing. This is delta F, this represents tone spacing. The total bandwidth would be whatever number of tones I have here times delta F. But in the time domain, the length of the block is 1 over delta F. And so we're going to see that in a second when we go to take a look at 3G and 4G. 3G and 4G. Especially 3G, let's come to 3G was based on using FFTs anywhere from 128 points to 2,048 points. This is an example with 128 points, but what's important here is delta F. The tone spacing is 15 kilohertz. This is 15 kilohertz, which means that in the time domain, if you go to the next page, in the time domain, it means that a length of each OFDM block is 1 over delta F, or 66.7 microseconds. And then they add on another 4.69 microseconds. This represents the buffer or cyclic prefix. And the total time of an OFDM block from here to here, including the cyclic prefix, is 71.4 microseconds, a very strange number. But this times 7 gives you half a millisecond. And half a millisecond was something that they were looking for. This 4.69 microseconds in terms of feet, if you think about delay spread, this represents something like 4,000 to 5,000 feet. So if you have delay spread more than 5,000 feet, you're going to have interference between one block and the next. So you choose this, so this is big enough. So if there is delay spread is not bigger than this number. Very important element. Anyway, we used in 3G, was used in 4G. Again, delta F fixed. Delta F is fixed at 15 kilohertz. In 3G, it could get up to a 20 megahertz bandwidth. You use 2,048 points. In 4G, you could get up to 100 megahertz basically by taking 5 of these 20 megahertz blocks. So where does 5G come in this? Go down another few pages. Okay. Okay. Just a few words about 5G here. What changed in 5G is the following. Instead of having delta F equals 15 kilohertz, which was fixed in 3G, fixed in 4G, you can change delta F. You can have delta F as 30 kilohertz, delta F 60, delta F 120, 240, even up to 480 kilohertz. Now think about it, if the FFT size remains the same, You start off originally with 15 kilohertz times 256 points. That was 1,000, let's say 2,048 points. And now suppose I increase the bandwidth by a factor of 4. The bandwidth, if I increase delta F by a factor of 4, the bandwidth of the total system can go up by a factor of 4. And so what happens, you can get tremendous bandwidth, but keep in mind that the time of an OFDM block is 1 over delta F. So the OFDM blocks become smaller and smaller, and with that, the cyclic prefix becomes smaller and smaller. Okay. It turns out in 5G and 5G NR, you can have 3,300 subcarriers, which ends up giving you a bandwidth of close to 400 megahertz. Okay, these we're using 400 megahertz. You're talking about signals that are being transmitted in the range of 50 gigahertz. Okay, where you have a lot of bandwidth. Okay, just to illustrate the point of this, if I come back here to the original 3G, 4G idea where you had a, let me go to the half, here's my half millisecond time slot. Each one of these is an OFDM block. This is my 71.4 microsecond OFDM block with a 4.6878 microsecond cyclic prefix. If I now, instead of using delta F 15 kilohertz, I now multiply this by a factor of 8 and go to 120 kilohertz. What's going to happen is that the size of my OFDM signals goes down by a factor of 8. So I originally had one of these, which was 71.4 microseconds. I now get 8 of these, and each one is 8.33 microseconds. And where the original cyclic prefix was 4.68 microseconds, it's now going to be divided by 8, and now it's 0.586 microseconds, which maybe is somewhere between 500 or 600 feet, which basically means if I go up, I use more and more bandwidth in 5G NR, which I want to do, transmit more and more bits per second. It also means that the cyclic prefix goes down. It means that I can withstand a smaller delay spread, which means I have to be operating in a place with a small delay spread, operating over small distances. But the big difference between 3G and 4G and 5G NR is the fact, basically, that I could increase delta F, increase the bandwidth, but decrease the cyclic prefix, less the robustness in the cyclic prefix. I have to use it over smaller distances. So that's where we are. Let me just sort of summarize where we are. Yeah, this is my summary. 5G is basically a very advanced version of 4G LTE. Basically the same modulation, just changed some of the numbers. Okay, the wide bandwidth here allow you to send tremendous bit rates, but you can only get these wide bandwidths if you go up in the range of gigahertz. So we're talking about the gigahertz range, 50 gigahertz, more or less in that area. The bottom line here, in my opinion, really 5G NR was, in terms of the physical layer, was really nothing new. It was sort of a replication of 3G, 4G, and now 5G. They're all using OFDM, OFDMA. So now we're ready to go and come to the 6th generation. First of all, I'm using his very famous name. There's nothing dangerous in this name, right? There's nothing dangerous involved here. I use this as my introduction to 6G. 6G, again, a year ago, when I mentioned this, when I was jokingly going to put up 6G in a talk I gave, and then I realized that I'd already been a conference on 6G. In fact, in February of 2019, this is the famous Donald Trump tweets, okay, in which you can read it for yourself over here. But basically, there's no reason that we should be lagging behind on something that is so obviously the future, which may be I don't want to get involved in politics, but maybe the smartest thing he said in the last few years. But basically, he was talking about 6G. What is 6G? It turns out really nobody has defined 6G, but everybody's talking about 6G. And this is a sort of quote that I took out of Professor Ari Patu, who's the vice director of a program, the wireless program, University of Oulu in Finland. They received $28 million, I think, from industry and the government to have what is called a flagship program. And in March of 2019, they had the first 6G conference. And he was quoted, and at the time, somebody asked him what is 6G. He says, and he's somebody who's the head of the program. He says, I don't know what 6G is, nobody knows. But people are trying to think about what 6G should be. First of all, this conference that I mentioned was in March of 2019 in Finland, University of Oulu. They were supposed to have another meeting this March, and because of the present situation, it was sort of a wireline meeting. But you can actually get on the internet and get some white papers that have to do with 6G. There was a conference in April of 2019 in Brooklyn called 5G, but there was a lot about 6G as well. And a friend of mine, Richard Gitlin, those of you know him, just recently sent this to me and said there's going to be a conference in October on the internet. I think InterDigital is one of the companies that's actually sponsoring this conference. So 6G is becoming very popular. On top of this, there's a whole bunch of articles coming out about 6G. So what are we talking about when we talk about 6G? First of all, we're talking about time frame of 2030 to 2035, which for some of us is very far in the future right now. And what I want to do, and almost every article you read has different reasons for 6G. And I could make a list a lot bigger than this, but smart cities, Internet of all things as usual, autonomous vehicles, robots, drones, virtual reality, telepresence, lightweight eyeglass instead of mobile phones. And in the end, I put apple pie because you can write down almost anything. I could have written down another 20 things I've seen in articles. But basically, the idea is you need a lot of bits per second. Okay? Again, nobody's really defined what 6G is, but everybody talks about data rates going into the range of terabits per second and very low latencies. And again, here's the whole business. When you read about latency, some articles talk about 1 microsecond latency. Some talk about 0.1 milliseconds. Some talk about 1 milliseconds. Even this number just depends on who you're listening to, but you're talking about a very small number. But the thing that interests me especially is this terabits per second. Talking about going up to terabits per second. Maybe it's almost hundreds of times bigger than what we're talking about right now. How can you get up to terabits per second if you get up to higher frequency ranges? Talking about using the ranges of between 300, 1,000 gigahertz, 1 terabyte, or even up to 3 or 4 terahertz. Why in this range you have tremendous bandwidths that are available. Talk about that in a second. Again, using massive MIMO and using something called large intelligent surfaces. Again, you can read up about this. Somebody introducing something called orbital angular momentum, another technique to try and get up to high bit rates. Everybody mentioning machine learning and artificial intelligence. Every article you read about mentions this. And we at this particular talk, we're interested just in the air interface. So let's continue. One of the first proposals made for modulation for 6G was made in the conference last year. The name of the article is called Air Interface Challenges and Solutions for Future 6G Networks. And basically they were proposing OFDM. So let me just show you this again. This is 3 slides that were taken out of that talk. The first slide essentially looked at 3G and 4G with delta F, the subcarrier spacing 15 kilohertz. The cyclic prefix, as I mentioned earlier, turns out to be 7% of the time of a symbol. This was 3G and 4G. Okay. Then this essentially was 5G. Instead of using 15 kilohertz, you could use numbers much bigger, 2 to the n times 15K, 30, 60, 120, 240, and even 480. And again, the cyclic prefix, the percentage of the block that's still a cyclic prefix remains the same. And what was their proposal for 6G? Their proposal was instead of using 15 times 248 and so on, just some number undefined, instead of having the cyclic prefix be 7%, some undefined percentage. But again, they were talking about using OFDM. But many people think OFDM, when you start getting up to numbers of terabits and terahertz, is not the way to go. There's going to be a lot of problem with DSP. And so they said, what other solutions can come up with OFDM? And a number of the papers that you read about, and I agree with a number of these papers, talk about using or going back to single tone modulation. Classic single tone modulation, some of it not so classic, but classic single tone modulation. And the reason is that when you get up into the terahertz range, you have some interesting properties. I don't know how many of you can see this, but if you look at this view graph, this essentially shows you the attenuation properties all the way up into the terahertz range. This is between 200 and about 300 gigahertz. And you notice here there's like a window. The bigger the higher you are here, the more the attenuation is. This is like a window. There's another window over here. There's another window here. And these windows are not small windows. Here you talk about 100 gigahertz. Here you talk maybe about 50 gigahertz. You have windows in which you can actually send the signal just imagine even a binary signal in a 50 gigahertz range. You're talking about 50 gigabits per second. So one of the ideas is, look, if we want to make something, we want to give simple receivers or simple transmitters and receivers, why not go back to single tone? And so the idea basically try and go back to single tone. A number of different proposals for single tone, classic constant envelope signal, we'll talk about this in a second. 16 QM, 64 QM, VPSK, QPSK, something called index modulation, which is really a combination of modulations. I want to say a few words about this. Talking about using faster than Nyquist signaling, which is a classic paper written in 1975 by Jim Mazo, which has come alive again in the last 10 years. A number of you are familiar with Jim Mazo was. People talk about pulse position modulations. There's some new idea called the OTFS that's out of a company in California. And this was just some implementation basically of a QPSK receiver. So what I would like to do is I'd like to go over at least the ones that I've outlined in yellow and say a few words about each one of these. These are single tone modulations. Again, the basis for using them is the fact that you have these windows close to 1 terahertz, which are windows which are 50 gigahertz wide, 100 gigahertz wide. And you're talking about simple modulations can give you tremendous bit rates. Now, if you can, throw a MIMO on top of that, so something else, and you really get tremendous numbers. So what I want to do is, first of all, just to give you an example of those who are not familiar with continuous phase modulation, as sure most of you are, but just probably the most famous one, just to give an idea of what we can accomplish. Is first of all, why continuous phase modulation? Continuous phase modulation is a constant envelope signal. We're talking about trying to save battery power. We're talking about making efficient use of the battery. Constant envelope, again, you can use a nonlinear power amplifier, efficient use of the battery. So these are very important modulations if you're talking about very, very wide bandwidth. A typical GMSK signal is you start off using a rectangular pulse stream, put it through a Gaussian filter, without getting involved in the whole business, but try and improve the bandwidth properties and use the signal coming out here to frequency modulate carrier. The output here is a typical FM signal, but has very, very good bandwidth properties. So let me just go down, show you what the bandwidth properties look like. These are the original paper written on GMSK almost now about 40 years ago. But if you look at the 99% bandwidth for almost all of the GMSK signals, just one second. For almost all of the GMA signals, the 99% bandwidth is equal to about 1 times the bit rate. It's not a very efficient use of bandwidth, but it still means if you give me a 50 gigahertz bandwidth, I can put 50 gigabits per second here. And I can use a continuous phase modulation, constant envelope, nonlinear power amplifier, efficient use of the battery. Single tone modulation, except what about BPSK, QPSK, even go up to 16 or 64 QPSK. Normally what we'd use for these would normally be Nyquist signals or square root Nyquist signals, and they get very good bandwidth efficiencies, but it turns out we can even improve that. Here's a typical 16 QM constellation. Again, normally we would transmit this using Nyquist baseband signaling. Okay, and normally what you would have is that the symbol rate would be equal to the bandwidth for using 0% Nyquist. If you use more than 0% Nyquist, so the bandwidth increases a little bit. But let's use 0% Nyquist for a second. The symbol rate equals the bandwidth. Get very, very good efficiency. Okay? But it turns out you can even improve the efficiency, and you can improve the efficiency by using an article that was written now, I guess 45 years ago, by Jim Mazo, and I think there are a number of you who knew Jim Mazo. Jim Mazo wrote this article 45 years ago, something called faster than Nyquist signaling. Normally you say faster than Nyquist means, oh, you're going to have a lot of intersymbol interference. Yes, you're going to have a lot of intersymbol interference. So let me give you an example here. If you take a look at this first top diagram over here, the top diagram is using perfect Nyquist signals, okay, 2W symbols per second and a bandwidth of W hertz. If you notice, you look at these, if you look at any instant of time here at this point, if you sample, all the sync functions go through 0 at this point. You sample, you get just this value here. At this point, everything goes to 0. You just get that value. Typical Nyquist signaling. But suppose now I go even faster. You know, the bandwidth is W and I transmit even more than 2W symbols per second. what's going to happen is you start getting into some interference. So just imagine having the same pulse, but transmitting instead of every 1 second, transmitting every 0.8 seconds. Same exact pulse. You're going to have intersymbol interference. And if you take a look at this, if I sample at this point right over here, not only am I going to get this value, I'm going to get the tails of these other signals. And you can say, yes, you're going to intersymbol interference. And so that's not good. Well, it turns out what Meso did 45 years ago, he says, let's take a look at the intersymbol interference. Let's take a look at it as if it's sort of a trellis code, you know, and let's say detect this using a Viterbi algorithm. And what becomes important is what is the distance between the signals. The distance between the signals determines the probability of error. And it turns out what he found out many, many years ago is that as long as you don't go 20% faster than the actual Nyquist rate, if you use a Viterbi algorithm at the other side and you look at the results you get, it turns out the distance between signals, the minimum distance remains the same as if you had no intersymbol interference. So this means you could actually go at a rate 20% higher than the so-called ideal Nyquist rate and still recover the signal with the same probability of error. If, again, you use you'd have to use now a Viterbi algorithm, but maybe many states, but it gives you an idea of what you can do. And it turns out in the last 10 or 15 years, a lot of people have looked at this as a way of improving bandwidth properties. So this is another new, not a new technique, but a new old technique that's been mentioned. One other thing I want to mention, which may be relatively new in terms of what we're talking about, this business of index modulation. A lot of us, many of us may not have been familiar with this, but index modulation is sort of very similar to MIMO, but it's a very interesting twist. Normally in MIMO, you'd have, on this side, you'd have, let's say, NT transmitters, the other side you have NR receivers, and then you transmit different information from each one of these on the same bandwidth at the same time. At the other side, hopefully you have a rich Rayleigh environment, and at the other side, you can actually separate all the signals in so-called MIMO without getting involved deeply in what MIMO is. But look what happens here. For each one of these antennas, you would need what's called a simple, different RF chain. Each one of these needs a different amplifier, different amplifier, different amplifier. So I would actually have NT amplifiers here. Now go to the next page, index modulation. What we do over here is we have, again, NT transmitting antennas on this side, but we don't use all of them. We only use NA of the NT. And it turns out, if you take a look at this, how many combinations can you have of NA? Suppose this is 8 and this is 3. How many public combinations can you have of 3 antennas if you originally had 8 antennas here? How many different 3 antenna combinations can you have here? And what you do is you assign to each one of these combinations, for example, suppose I could have 8 different combinations. 8 different combinations means 3 bits. So at the other side over here, not only am I detecting the actual modulations, but I'm actually trying to figure out which of the antennas was used. And if it could have been one of 8 possible antennas or one of 16 possible antennas, it's an extra 3 or 4 bits. And so it turns out this is an interesting way of having more bits. And it turns out I don't have to use all of these antennas. All I'm using is just NA of the NT antennas. And this NT could be a very big number and NA could be a pretty small number. And it turns out a number of people started working on this. And a lot of these papers are from last year, this year. There were a lot of these. And this is a typical example of different modulations that we use. In this case, which is this curve right over here, which is a pretty good result without getting involved. But this is a pretty good result compared to the other result. They were using this as CPM, continuous phase modulation, with a raised cosine pulse. They were using a 4-area system. In this case, the best one there, they're using differential QPSK, 2 bits per symbol. Okay, these two get very, very good results. In these cases, all the way up here, the modulation we're using 256 QM. In the 256 QM, but they were only picking 2 antennas out of a possible 24. But it turns out these results give very, very good results. What's nice about this, the one that are using continuous phase modulation means, again, you can use a nonlinear power amplifier to transmit the signal. And these, the QPSK, you could probably reduce the peak to average of these as well. So there's another interesting way here of trying to get a lot of bits per second. And again, once you're talking about bandwidths of 20 gigahertz, 100 gigahertz, you're talking about lots of bits per second. Okay. This is just in the last 2 or 3 years, a lot of people are trying to implement these different systems at high frequency. This is a view graph. If you want, I can send you a note. But this is a view graph essentially showing many, many results from many, many papers in the last few years. 120 gigabits per second. Look at the numbers here. At 400 gigahertz using QPSK. Each one using a different technology. If you go one page further, this is just now. I just picked this up a few weeks ago. This is out of a paper. 115 gigabits per second at 0.3 terahertz over a different distance. I should say of 110 meters. This is something implemented. People actually building it. This is another article just came out about a month or 2 months ago. A different way of implementing the actual transmitter and receiver. 100 megabits per second at 90 gigahertz. The basic thing that's going on here is a lot of people are trying to figure out how to actually implement these systems at rates of, at frequencies of 300 and 500 and 1 terahertz using very simple modulations. Very simple modulation, not using OFDM. This is sort of a new concept. So let me just summarize it all. If we talk about 6G, people are talking about going up to bit rates of terabits per second. It means you have to go up to very, very high frequencies, and we're talking about terahertz frequencies. So we're talking about hundreds of gigahertz and even more, okay? That's number one. In my opinion, this probably has to be some new work done on single tone modulations. A field that's been very quiet for many, many years, especially continuous phase modulations, okay? OFDM may still be suitable at lower frequencies. Not everybody's going to operate at terahertz. Again, what I would consider single tone modulation, CPM may be a very, very good solution. And right over here, it says many organizations are already working. There are papers coming out all the time on 6G, even though people are talking about 6G in another 10 or 15 years. Even papers talking about actually reducing it, maybe another 5 years, maybe not another 10 years. Maybe 6G will pick up all the problems of 5G, try and solve them. So this is where we stand right now. And then the last thing, it was an article came out a little over a year ago called What About 7G? So I don't know if anybody wants to get interested in 7G, it's up to you. But I would basically like to summarize this by saying that 6G terahertz is a new world. New world in terms of maybe modulation, new world in terms of information theory, and a new world certainly in terms of implementation. Okay? That's all I have to say. I guess there's a very hard way of getting questions, but let me take a look and see if there are any questions.
So I'll just remind the participants that, especially those who came in late, that unfortunately there's no way in which you can speak and be heard. So the only way you can communicate with Irving is by typing your question. And I suggest you use the Q&A window, which is at the bottom of your, somewhere in your screen, Zoom screen, Q&A. Type it in. I see there are already 2 questions. And Irving will look at those questions and read it out and respond to them.
Okay. First of all, one from Steve Weinstein. Hi, Steve.
Yeah.
Will 6G phones no longer be backward compatible with early generations? I think that depends on who builds the 6G phones, because every time you build one generation, they try and make it back compatible. I would imagine it would be. Okay? That's answer the first question. Second, hi, Yanis. Question, could this massive use of electromagnetic bandwidth weaken the Earth's magnetic field and make us susceptible to cosmic radiation? Yanis, I have no answer. I have no idea. So, I hope maybe other people know, not me. Sorry. Next question from Woodrum Lee. I missed why OFDM is not a good choice at millimeter wave terahertz. Basic reason there seems to be is the DSP. People claim it may be very, very, very hard to do DSP at these frequencies. That's the basic reason you see given for this. Next question. Will you provide a view graphs to the audience? Yes. Anybody who wants one, yes.
Yeah, well, you can write directly to Irving or write to me and I'll pass it
Next question from Yanis Tsividis. I didn't ask that question. Which Yanis was it? I thought it was you, Yanis. Sorry.
All we know is that other Yanis was also from New York City.
Okay. Next one from Peter Kingett. In index modulation, at what rate do you change the index compared to the data rate? Well, to be honest, I don't know, but I would imagine it would have to do with the speed at which the channel was changing. Because you also have to, at the receiving side, you have to know what the channel characteristics are. So I would imagine it would have to be faster than the rate of change. Michael Malari, 1 second. What are the implications of extremely high frequencies on mobility, traveling on high-speed train, and density, Times Square or stadiums? Oof, I've never thought of it, so I could probably give you a back of the envelope answer, but I've really never thought of it. So I could imagine high-speed trains is going to be a problem, but I have to think about it. Anybody else with a? As far as I can see, no other question. I hope that I got some of you interested in 6G. It seems to be becoming a very, very, very hot topic throughout the world. Debasis, you would?
Well, Irving, you know, as Peter says, thanks. It was a most interesting talk on many dimensions. And really great to hear you. Great to hear your perspective, especially the historical dimension and all that. So, thank you very much. So, last chance if anyone has a question. Otherwise, I don't see any more questions. Oh yes, no. I guess that's it. Thank you.
That's it.
Thank you, everybody, for participating. Quite an audience.
Thank you, Debasis. Thank you. Thank you, thank you for coming. Bye.
Bye, everybody.